definition of the eigenvalue and eigenvectors, and then how to solve the find the eigenvalues and eigenvectors. Do you still remember how? So the definition is that we need to find the special vectors and numbers such that ax equal to lambda x, right? So x is non-zero vectors. So in order to make sure that ax equal to lambda x has non-zero solutions, we need to make the determinant a minus lambda I equal to 0. This is the characteristic equation, and we can use this equation to find the eigenvalues. After finding the eigenvalues, we just substitute the eigenvalue to the equation ax equal to lambda x and find the corresponding eigenvector. And for those eigenvectors, we have an important property is that if we have r distinct eigenvalues, then their corresponding eigenvectors are linearly independent, right? So those are very important properties. And in today's lecture, we will go further and utilize those properties and the derived eigenvalue, eigenvector to do the matrix decomposition. A special matrix decomposition, it is called the diagonalization. What is diagonalization? Let's see, a special matrix, D is a diagonal matrix. Let's see what the special property do we have. Look, if D equal to 5, 0, 0, 3, then if we can calculate D square is 5003 times 5003, and then you can see that we just follow the general ideas on how to do the matrix multiplication, and you will see the result is very simple. We just take the square on the diagonal elements, right? And this is not only true for D square, it's also true for D cubed, and actually in general, D power k just equal to 5 power k, 3 power k, and the off-diagonal elements keep 0. So this is a very important property. And in the last lecture, we also discussed a special definition is that the similarity, right? And we have called that two matrices are similar to each other if A equal to P inverse BP. Remember this formula? And in last lecture, we didn't mention that special form of the B. Actually, if matrix A is similar to a diagonal matrix, look, A equal to P dP inverse, P is invertible and D is diagonal, then A square, and it's easy to calculate A square as well. You can see that A square, A is P dP inverse times P dP inverse, right? And then here is P inverse can be cancelled out. And this is equal to P d square P inverse. And in general, A power k equals P dk P inverse, right? Now, let's see this example. Let A equal to this matrix 7 to negative 4, 1. Find a formula for A power k given that A equals P dP inverse, where P is equal to 1, 1, negative 1, negative 2, and D equal to 5, 0, 0, 3. So let's see this example and special example and do some calculation. You have better ideas. We do it together here. So because we needed to find the P inverse, we need to do the multiplication at home. So this is a 2 by 2 matrix. Do you still remember look for a matrix A, B, C, D. Do you remember the A inverse, the formula for A inverse? which is equal to AD minus BC, right? 1 over AD. And then here is the opposite, DA, AD, DA, and then negative B, negative C. Do you remember this formula? Okay, so we can use this formula. It is easy to see that P inverse should be equal to 1 over 1 times negative 2 minus 1 times negative 1. And then here is negative 2, 1, and negative 1, 1, right? And this is negative 2 plus 1 is negative 1. So we have 2, 1, negative 1, negative 1. So A square equal to P D P inverse P D P inverse, which is equal to P D square P inverse, and which is equal to 1, 1, negative 1, negative 2 times D square is 5 square, 0, 0, 3 square, times 2, 1, negative 1, negative 1, right? It's like this. But our problem is not a square, AK. Now you can see that similarly, AK should be just equal to P, D, K, P inverse, right? And this is equal to P is equal to 1, 1, negative 1, negative 2 times 5 power k, 0, 0, 3 power k. 2, 1, negative 1, negative 1. So then we do the multiplication. And it's easy to find the final result. 2 times 5 minus power k, 3 power k, 5 power k minus 3 power k, and 2 times 3 power k minus 2 times 5 power k, and 2 times 3 power k minus 5 power k. A square matrix A is said to be diagonal. So this phenomena is very important, and you can generalize it to like matrix higher order n by n, right? So we give this type of procedure a name. So how to decompose a matrix A into a invertible matrix P times diagonal matrix times P inverse, like this. Okay, so we call this is diagonalization. So a square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. So here, earlier similarity is the definition. We don't have any special constraint on A and B, right? But the diagonalizable and then we need to make sure that the A is similar to a diagonal matrix. That is, if A equals P D P inverse for some invertible matrix P and some diagonal matrix D. Okay, and then we will discuss the diagonalization theorem. So this theorem actually tells us how to find this invertible matrix P and diagonal matrix D. So actually, it's very simple. N by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So as long as you can give me n linearly independent eigenvectors, if I know it, then we know their corresponding eigenvalues as well, right? And using those information, I can construct the matrix P and construct the diagonal matrix D. How to construct? It's very simple. The matrix P actually is each column is those eigenvectors. Because those eigenvectors are linear independent, so P is invertible. That makes sense? And what's the diagonal elements? They are corresponding eigenvalues. So I will give explanation now. Here. Look. If, so I can give you the proof and then you can, because those are so all sentences, it's not so easy to understand at the very beginning, so forget about it. We just focus on this formula, this sentence. This is the thing you really need to know, right? So if A has n linearly independent eigenvectors, then A is diagonalizable. So let me show you why. So let V1, Vn be the n linearly independent eigenvectors. Then there exists lambda 1, lambda 2 to lambda n, such that actually these are their eigenvectors, eigenvalues, right? We have AV1 equal to lambda 1 V1, right? AV2 equal to lambda 2 V2, to AVN equal to lambda n Vn. So I just let P equal to V1, V2, Vn. Okay, we can write down these formulas, these n formulas in the matrix form is AP equal to P times D, or P lambda 1, lambda 2 to lambda n. Written in this way. Okay. So in the last lecture, some students asked me that why we put the diagonal matrix on the right rather than on the left. Okay, I give you a very simple example to show the difference. And here, look at this. I just show you a very simple example. We just consider 2 by 2 matrix. Okay, so actually it's the same. Or you can consider 3 by 3. It doesn't matter. For example, I have a matrix B, which is B11, B12, B13, B22, B23, B21, B23, B21, B22, B23, B31, B32, B33. And I give you a diagonal matrix, maybe lambda 1, lambda 2, lambda 3. Okay, so here, this example, I just want to show you that the difference of B times D and D times B. Okay? Then you will see why I do it this way. Okay, let's see B times D. What's the result? B11, B12, B13, B21, B22, B23, B31, B32, B33. If I multiply lambda 1, lambda 2, lambda 3, you will see you just do the general operation like matrix multiplication. Look, this times this, so I just get lambda 1, B11, right? And then here is lambda 2, B12, lambda 3, B13. And then next, this row times this one, we get lambda 1, B21, lambda 2, B22, lambda 3, B23, lambda 1, B31, lambda 2, B32,
lambda 3, B3, 3.
Do you see what's the effect? So if I multiply the diagonal matrix on the right-hand side, we do the scaling for each column. We are doing the scaling for each column, right? And what's the scaling number? The first column is first element, lambda 1. Second column is lambda 2. Third column, lambda 3. Okay, so but if we multiply it on the left,
so due to the space limitation here, I put D directly here. Okay, let's see DB, which is equal to lambda 1, lambda 2, lambda 3. What's the effect? You can see this is lambda 1, B11, lambda 1, B12, lambda 1, B13, lambda 2, B21, lambda 2, B22, lambda 2, B23, and lambda 3, B31, lambda 3, B32, lambda 3, B33.
Do you see? What's the difference? If I put the diagonal matrix on the left, we do scalings for each row. First row times lambda 1, second row times lambda 2, third row times lambda 3. Do you see the difference? Left, right. Okay, now we go back to previous example, previous one. So look at this formula, you can see, because V1, V2, V3, they are columns of matrix P, right? And here lambda 1, V1, lambda 2, V2, lambda n, Vn. What we do is scaling is for each column. That make sense? So more specifically, if you don't see it directly, I can now let you know this one. So I can put this one on the right here. So this formula here, and if I want to make this in the matrix form, you can also see A times V1, V2. So maybe you can return like this. A times, you can return like this. V1, V2 to Vn equal to lambda 1, V1, lambda 2, V2 to lambda n, Vn. So this is exactly P times do the scaling for the lambda 1, V1, right? And the left hand, this is exactly A times P. So it's more clear now, right? So earlier, it's n different formula. I written in the matrix form, I just put them together. This is doable, right? You just correspond each column. The two matrices are equal, which means the corresponding columns should be equal, right? So, and then this, if I let the matrix P to be V1, V2, Vn, then AP equal to PD. If D is a diagonal matrix, lambda 1 to lambda n. So more specifically, so if I discuss this, the matrix D here, denoted to be lambda 1, lambda 2 to lambda n, then here this one, you can return in PD. So we get a formula AP equal to PD. And P is this matrix. AP equals to PD, right?
formula is equivalent to A, P, D, P inverse, right? I multiply both sides by P inverse, we get this one. This is the decomposition we are looking for. So A is similar to D. So if you understand those reformulations, those formulas, you can see all those formulas are equivalent to each other, right? So that's why A is similar to diagonal matrix if and only if A has n linearly independent eigenvectors. The proof is clear. So I didn't do anything. I just use different notation. That's it, right? The only thing I do is that AP equal PD is equivalent to A equal to PD P inverse. That's it. And all other steps, I didn't do anything. So this proof obviously help you understand how to do the diagonalization, right? So the first step, we find all the eigenvalues and then their corresponding eigenvector. And then check if we do have n linearly independent eigenvector. If so, then we just let the invertible matrix P to be V1, V2, V3 to be n, right? And D just to be the corresponding eigenvalues. But those eigenvalues should have the order. Look, the P, V1, then the D is lambda 1, okay? V1, lambda 1, they should have correspondence. You should not switch the order of those lambdas. That's incorrect. The proof obviously shows this one, right? You needed to put everything in order. Because the formula we have is AV1 equal to lambda 1 V1. AV1 not equal to lambda 2 V2, right? So AV1 equal to lambda 1 V1. So you needed to put everything in order. If you put P is V1, V2, V, but you can, some student may ask, could I put like the order P to be V2, V1, V3, Vn? Because sometimes some students get the lambda 1 equal to 3 first. Some students get lambda 1 equal to 2 first, right? Can we switch the order? Yes. But if you switch the order for the P, you also switch the order for the D. That's it. So the solution is not unique for sure, right? Because you can always switch the order of the P. I can switch V1, V2, or V1 with V3. Doesn't matter. Because in real application, what you get is the true numbers, right? You are not able to say this is V1, this is V2. Some students would like to let the first eigenvector he gets is V1. But another student maybe, because when you calculate eigenvalues, then maybe there's two eigenvalues. One is equal to 3, one equal to 2. So some students denote lambda 1 equal to 3, lambda 2 equal to 2. But some students would like to let lambda 1 equal to 2, lambda 2 equal to 3. So the result they get could be a little bit different. But the basic one is the same. If you switch the order for P, you switch the order for D as well, right? You still have their correspondence. So eventually the results are the same. But this same means that they got the same matrix A. Okay? That make sense? Okay, so now we will do some exercise, some examples to show this theorem how to do the diagonalization. So let's see this example. Diagonalize the following matrix if possible. A is 1, 3, 3, negative 3, negative 5, negative 3, 3, 3, 1. That is, find an invertible matrix P and a diagonal matrix D such that A equal to P, D, P inverse. How to solve this type of problem? So after previous theorem, you should have a rough idea that first we need to find eigenvalues and their eigenvectors, right? And then you put P to be the eigenvectors, D and the corresponding eigenvalues like this. So let's do it step by step. eigenvalues. We have this a minus lambda I. So then what's the next step? So we can follow the general ideas. We do the echelon form, right? So we switch the order of the first row and the last row, like the way we did in the last lecture. But for this example, there are something special. Do you notice that negative 3, if we add them together, we got exactly 1, 0 first, right? So maybe we get 1, 0 first to see what it looks like after doing this way. So actually, after doing this way, we get some special thing, and this will further simplify the calculation. So negative 2 minus lambda, negative 2 minus 3, 1 minus lambda. So look, what's happening? Do you notice what's happening? Yeah. We have a common factor, we move it out first for sure, right? Digit lambda 3, 0, 1, 1. 3, 3, 1 minus lambda. So next is that you may notice I can make it 0 or 0 in the first row, right? So the key portion is because they are exactly the same. It is proportional to each other. So negative 2, negative lambda. And then here is 1 minus lambda, 0, 0. 0, 1, 1. 3, 1 minus lambda. Look, now we have 2 zeros in this row, so we can expand it directly. So which is negative 2 minus lambda times 1 minus lambda. 1, 1. 3, 1 minus lambda. So we get the lambda minus 1, lambda plus 2. Here is negative lambda minus 2 as well. So this is negative lambda minus 1 times lambda plus 2 square. Now we just find linearly independent eigenvectors of A. So for eigenvalue lambda 1 equal to 1, we solve a minus lambda 1I times x equal to 0. We solve this homogeneous equation to find the corresponding eigenvectors. So then here you just copy this matrix, right? So this is a minus lambda I matrix. This is our matrix. And here lambda replaced by lambda 1. Lambda 1, the value is 1 here. So here is minus 1, minus 1, minus 1. So now we get 0, 3, 3, negative 3, negative 6, negative 3, 3, 3, 0, 0, 0, 0. So we do the row operation with because this element is 0, so we need to do that. Because the first column is pivot column for sure is not all 0. So we need to swap the first row and the last row. And then we do the scaling. Then the second row also the same. So 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0. We got this one. So this one you can get the equation x1 minus. Okay, sorry. We further. This is not the reduced echelon form, so we need to make this element to be 0 further. So we got 1, 0, negative 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. Then we get the equation x1 minus x3 equals 0, x2 plus x3 equal to 0. And then we got x1 equal to x3. x2 equal to negative x3. Okay, so the solution is x1, x2, x3, which is equal to x1 equal to x3, x2 equal negative x3, which is equal to x3. Here is 1, negative 1, 1. So then we choose V1 equal to 1, negative 1, 1 as an eigenvector. Okay, so this is corresponding to. So here I also reviewed how to find the eigenvalue and their corresponding eigenvectors. So for eigenvalue lambda 2, we do the same thing, so but I omitted details here, okay? For lambda 2 equal to negative 2, we need to solve this homogeneous equation a minus lambda 2I x equal to 0. So due to time limitation, I omitted details. So the equation is 1 plus 2, 3, 3, negative 3, negative 5 plus 2, negative 3. 3, 3, 1 plus 2, 0, 0, 0. So this is equivalent. Eventually will equal 1, 1, 1, 0, 0, 0, 0, 0, 0. So we get x1 plus x2 plus x3 equal to 0. So the solution is now we take V2 just be this one. So for this eigenvalue, we have an eigenspace is dimension 2 and the spaces is these two vectors. Corresponding to eigenvalue 2. Now, although here we have only 2 eigenvalues, but we still have 3 linearly independent eigenvectors, right? We have a theorem we proved earlier that even though that we have the repeated eigenvalues, we don't have 3 distinct eigenvalues, we only have 2 distinct eigenvalues, but we still have 3 linearly independent eigenvectors. In this case, the matrix A is still diagonalizable, right? And the V1, V2, V3 is linear independent. It's for sure. We proved this theorem in the last lecture. Do you remember? Right? And in that theorem, actually, is even more general. We have 3 different eigenvalues, but 4 linear independent eigenvalues. So this V1, V2, V3 are linear independent for sure. And you can even prove it because this V1, V2, V3 is given. You can double check it if the matrix is determinant not equal to 0 or 0. Okay? But what I can tell you according to the theorem is for sure V1, V2, V3 are linearly independent. Now we construct P. So P equal to V1, V2, V3. So which is equal to 1, negative 1, 1, and negative 1, 1, 0, and negative 1, 0, 1. So the determinant of P just equal to 1 times negative 1, 3 plus 1 times 1, 0. So here I expand it through this row, okay? And here I just want to show you that this determinant, they are linearly independent for sure, okay? But here I can double check it for sure. And negative 1. So actually, in the lecture notes, I use this row. So I just keep with this row. Okay, it doesn't matter too much. 3, 1 here is, so you delete this one and this column. So we got negative 1, negative 1, 1, 0. Plus 1 times negative 1 here is 3 plus 3, right? And then in this case, this row, this column, so it's 1, negative 1, negative 1, 1. So this is overlapping on them, right? So they are linear independent indeed. But in exam, you don't have to write down this portion. This one, here in class, I want to double help you understand it better. But this is not necessary for this portion because for different eigen, even repeated eigenvalues, we get the eigenbasis, right? Those are linear independent. Then it's also linear independent with another vector here. So V1, V2, V3 is linear independent for sure. So determinant of B, T should not equal to 0 for sure. Okay, you don't have to check it. But here I double check it just to ensure you, yes, they are linearly independent. Okay, now we can construct the D. The step 4. We got this one. Okay, so why I use here V1, so that's why lambda 1, right? V2, V3 corresponding to lambda 2 here. Then here is let me see. It's okay, sorry, here is a typo here, negative 2. So here that's why we have negative 2, right? Okay. So now, could you go ahead and solve this problem? So here, for this type of problem, it says diagonalize the foreign matrix if possible. So in other words, if you cannot find the 3 linear independent eigenvectors, then it's not diagonalizable. Okay? So you need to keep it in mind. So it's not always diagonalizable. So if you find it's not diagonalizable, it's also this is also a possibility. Okay, so hopefully you have get the eigenvalue, eigenvectors. So in this example, so look at this one. So this matrix, so we calculate eigenvalues by using this formula. And actually, for this one, we can also still use some special way. Because look at this, the first two, you can see the 3, -3. If you add them together, it's 0 again, right? The right hand. And then you also get -2 minus lambda, -2 minus lambda. Do you see? So we can use the same way we did for like earlier. But here, in this example, I use the general way. The general way is that you just find a pivot. In the pivot position, I would like to choose scalar, so number 3. So I swap the first row and the last row. And then we do the scaling to make it 1 because here there's first columns, there's no common vector here. Okay, so we get 1, 0, 0, and then you can see that here, and then I can do the the expansion according to the first column, and then we get this small matrix. This small matrix here is 2 by 2 and have common factor in the first row, right? First column, lambda plus 2. So I move it outside, it becomes this one, and then we do the simplification, and eventually we get this formula. And I have mentioned how to do this factorization, right? So this one you can put a negative in front, 3 lambda plus 2 times lambda squared plus lambda minus 2, okay? So then we get this one. So the eigenvalues are lambda 1 equal to 1, lambda 2 equal to -2 here. So for lambda, now for lambda 1 equal 1, we just solve a minus lambda 1I identity times x equal to 0. So we have this one, and 2 minus 1, 4, 3. -4, -6, minus 1, -3. And 3, 3, 1, minus 1 here. So get x1, x2, x3. And this is equal to 0, 0, 0. So you just for this matrix 1, 4, 3, -4, -7, -3, 3, 3, 0. And this 0, 0, 0. So we do the row operation is 1, 4, 3, 0. 0, 9, 9, 0. And 0, -9, -9, 0. Okay. So it's obviously 1, 1, 0, 0, 0, 0, 0. 1, 0, -1, 0. 0, 1, 1, 0, 0, 0, 0, 0, right? So it's very easy to get the equation x1 minus x3 equal to 0, x2 plus x3 equal to 0. So we got x3, negative x3, x3. So we got x3, 1, -1, 1. So choose eigenvector v1 equal to 1, -1, 1. For eigenvalue lambda 2 equal to -2, of A minus lambda 2 identity x is equal to 0. Okay, so we have 2 plus 2, 4, 3, 0. Negative 4, negative 6 plus 2, negative 3, 0. 3, 3, 1 plus 2, 0. So this is equal to 4, 4, 3, 0, negative 4, negative 4, negative 3, 0, 3, 3, 3, 0. So I go a little bit fast and don't explain so much because this is the echelon form, reduced echelon form. We repeated so many times, right? So we eventually get this one. So this one, the equation tells us x1 plus x2 equal to 0, negative x3 equal to 0. This actually tells us x1 equal to negative x2 and x3 equal to 0. So here is the solution. Equal to negative x2, 0, which is equal to x2, negative 1, 1, 0. Now choose eigenvector. So look, how many eigenvectors do we have altogether? But that's all the eigenvalue we have, right? We have only 2 eigenvalues here because lambda 2 equal to negative 2 is repeated. The multiplicity is 2. But even for multiplicity 2, the corresponding eigenvector, there's only 1. So altogether, how many linear independent eigenvectors? Only 2. How many linear independent eigenvectors do we need to diagonalize the matrix? 3, right? So can we do the diagonalization? No. So in this example, we are not able to diagonalize the matrix A. So here A. So I would like to make it more clear. There are no other eigenvalues, right? And every eigenvector of A is a multiple of either V1 or V2, right? Hence, it is impossible to construct a basis of R3 using eigenvectors of A. So A is diagonalizable. Okay, now here's the thing. Then, under which condition A is diagonalizable? We already discussed that it has n linearly independent eigenvectors, right? When can we have n linearly independent eigenvectors? One special case we discussed in the last lecture is that it has n distinct eigenvalues. Then each eigenvalue corresponding one eigenvector. So altogether they have n distinct linear independent eigenvectors. So that's why we have this theorem. An n by n matrix with n distinct eigenvalues is diagonalizable, right? So this theorem is very simple. Now look at this one. Determine if the foreign matrix is diagonalizable. Can you determine directly without any calculation? And tell me why. Can you determine? So look, this is triangular matrix, right? This is triangular matrix, and for triangular matrix, we know the eigenvalues. The eigenvalues are just those diagonal elements, right? So for this diagonal elements is 5, 0, -2. So which means for this matrix, we have 3 distinct eigenvalues, and they should have, according to the theorem we just discussed, it has 3 linear independent eigenvectors. So this is diagonalizable, right? So, yes. But in the exam, you need to give me the reason, okay? So like the way we did in the lecture notes. So we just say because the matrix is triangular and its eigenvalues is 5 to -2, they are distinct with 3. So this is 3 by 3 matrix with 3 distinct eigenvalues. So that's why A is diagonalizable. Okay, you give me the reasons. So due to time limitation, I don't write down it clearly. You can check the lecture notes. So now here, so how about that eigenvalues are not distinct? We discussed 2 special examples, and in this example, in this one, you can see in the first example, and here we have only two eigenvalues, and the one eigenvalues is with multiplicity 2. But in this example, and we do find 3 eigenvectors. So that's why in this example it's diagonalizable, right? So in this example, actually the eigenvalue repeated twice, multiplicity 2, but they have 2 corresponding eigenvector, a basis, linearly independent eigenvector, right? 2 linear independent eigenvector. But actually for eigenvectors, they have infinitely many because any combination of those lead one to are still the eigenvectors. But we want to check this eigenspace. What's the basis, the dimension of eigenspace, right? So for lambda 2 equal to -2, it's repeated twice. They have 2 linearly independent eigenvectors. So that's why we can diagonalize. So multiplicity is consistent with the number of bases of the eigenspace, right? But is it possible that if multiplicity is 2, but the eigenvector only appear once? Yes, this is possible. Look at this example, you can see that eigenvalue is 1 negative, so here's only 2 eigenvectors. In this case, it's not diagonalizable. So for repeated eigenvalues, so some cases is diagonalizable, some cases is not diagonalizable.
So under which conditions they are diagonalizable and under which conditions they are not diagonalizable. That's the one. This is theorem we are discussing. Okay. So let A be an n by n matrix whose distinct eigenvalues are lambda 1 to lambda p. For k from 1 to p, the dimension of the eigenspace for lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. So this is a fact. So actually, the dimension of the eigenspace actually could be equal or less than to the multiplicity of the eigenvalues. So we have an example shown before, right? So multiplicity is both those examples. The multiplicity of the eigenvalues is all 2, right? But the corresponding, the dimension of eigenspace could be 1 or 2. So less than or equal. And so the matrix A is diagonalizable. We know if and only if we have n linearly independent eigenvalues, right? So actually, how many the repeated multiplicity of the eigenvalues? So corresponding eigenvectors they should be equal. If equal, then we can still get n linearly independent eigenvectors. So this is the case. It tells us that when so the sum of dimensions of the eigenspace equals to n altogether. So which means we have n linearly independent eigenvectors. So then under which condition this will happen? The characteristic polynomial factors completely into linear factors. So which means that the characteristic equation is a polynomial degree n. We have n real solutions. If we count the multiplicity, we should still have n real solutions, not complex solutions, right? Because like for quadratic equation, sometimes we don't have real solution. Like for example, x squared plus x plus y equal to 0. We don't have real solution. We cannot further factorize it to linear terms, right? So that's why we need to make sure that the characteristic equation can be all factored into the linear terms, even including the multiplicity is not matter. And the next is that the dimension of the eigenspace for each lambda k should equal to the multiplicity of lambda k. If these two happens, then we can make sure that even the eigenvalues are repeated. This we still have a linearly independent eigenvectors. Then in this case, it is still diagonalizable. So this is the thing. So it looks like very long, but it's easy to understand. You just keep these two examples in mind, then you have good ideas. Okay. So the key portion is that we need n linearly independent eigenvectors. So if the eigenvalues are repeated, then how to find n linearly independent eigenvectors? That's the thing. Okay. So you need to check what's the condition. Now let's see next one. If A is diagonalizable and Bk is the basis for the eigenspace corresponding to lambda k for each k, then the total collection of the vector in the set form an eigenvector basis for Rn. That's for sure, right? Because those are linearly independent vectors. So they are corresponding, so the basis. Now let's look at this example. Diagonalize the following matrix if possible. So this is a large triangular matrix, and so the eigenvalues is easy to find. So we just write down the eigenvalues directly. And so for okay, sorry. Then for the corresponding eigenvalue vectors, so I just give you the result. And can you help me write down the matrix P and the diagonal matrix D? So this is, but in exam you need to solve the equation for sure, okay? So since A is a triangular matrix, the eigenvalue
multiplicity 2. For lambda 1 equal to 5, solve a minus lambda 1 I, then x equal to 0. We can get for lambda 2 equal -3, solve a minus lambda 2 identity x equal to 0. We can get the basis V3. So here you solve this homogeneous equation. So we just omit the details because those portions we are very familiar by now. So, but in exam you need to give me the details. Don't write down those eigenvector directly. Okay. So the set is V1, V2, V3, V4 are linearly independent. Now, based on this fact, could you construct the matrix P and D? What's the P? What's D? Simple, right? So P here is just -8, 4, 1, 0. -16, 4, 0, 1. 0, 0, 1, 0. 0, 0, 0, 1. And D is just 5. 5. Okay. Now let's see, show that if A is both diagonalizable and invertible, then so is A inverse. Can you prove it? A is invertible, A inverse also invertible for sure, right? So A is diagonalizable. What's the meaning of diagonalizable? So you just check A is diagonal, P, D, P inverse, right? This meaning of diagonalizable. Then A inverse, let's check is P, D, P inverse, the inverse, which is equal to P inverse inverse, D inverse, P inverse. So it's equal P, D inverse, P inverse. And the D inverse, diagonal matrix, the inverse, is still diagonal matrix, right? That makes sense? And because A is invertible, so the diagonal entries of D, there's no 0 involved. The determinant of D is not equal to 0 for sure. So that's why here A inverse is also invertible and diagonalizable, right? It's very easy to check. Now let's see this one. Show that if A has n linearly independent eigenvectors, then so does A transpose. So A has n linearly independent eigenvectors, which means A is diagonalizable, right? And A is diagonalizable, so we have the formula. So in the lecture notes, there's something wrong. Okay, A is diagonalizable, so it means P, D, P inverse. Okay, and then A transpose, which is equal P, D, P inverse transpose, which is equal P inverse transpose, D transpose, P transpose, which is equal P transpose inverse D, P transpose. You just let an invertible matrix Q plus equal to P transpose inverse, right? Then this is Q, D transpose, and Q inverse. So this is diagonalizable. Clear? Now look at this example. A is this matrix. Find the range of A where A has no real eigenvalues. How to check the eigenvalues? Determinant A minus lambda I equal to 0, right? So which is 1 minus lambda. A 1 minus lambda equal to 0. So then we can simplify it. It's equal to, so 1 minus lambda square minus A, which is equal lambda square minus 2 lambda plus 1 minus A equal to 0. So then how to make sure there's no real eigenvalues? It's something like we have delta, right? Delta equal to B square minus 4AC. This is less than 0, which is equivalent to say A is less than 0. Okay, so we get the result. Okay, so due to time limitation, we just stop here today. And in today's lecture, we just discussed how to diagonalize a matrix A using eigenvalue and eigenvectors. So there's a real example, so due to time limitation, we will leave it in the next lecture. So that's all for today's lecture, and see you next week.